Oh, hi. Pre-calculus, how's it going? Week 4 coming at you. We learned about parametric equations last week and how it's a third parameter, and we still got some of our conic sections, and that's why it's in the conic section chapter that it is. And similarly, you guys are going to get something new today called polar coordinates, and you're going to see some conic shapes show up in this stuff as well. So eventually. For now, though, we just need a quick introduction. What is it? Okay, you guys are used to Cartesian coordinate system, a rectangular coordinate system. Rectangle because you go an x coordinate and you go a y coordinate, and you can get to a point. Well, it's not going to be like that in polar coordinates. In polar coordinates, we get how far away from the pole we are, North Pole, South Pole, how far away from the pole we are, and at what angle, right? Think circles and things. So it's a whole new graph. It's a whole new graph system. It looks like a bullseye with a bunch of concentric circles. Concentric circles were part of your challenge problem this week, but let's dive right into it and get into this. So I'm going to switch it over to my document camera, and very first thing, I'm just comparing what we know. Rectangular coordinates there, those ones in blue, they make rectangles, right? Left and right, 90-degree angles. So we have how far over in the x, we have how far up in the y, and we get this ordered pair for rectangular coordinates, a spot in space. Well, we can get to that same spot in space if we know what direction to aim, where am I going to face, and then how far out am I going to walk. Those are the two things we need, and we can still get to the same point. So part of our notes today is going to be about going back and forth between the two. If I give you a point in rectangular coordinates, you need to be able to find how do I describe that point in polar coordinates, and vice versa. So x and y old, r and theta new. Let's get into it. First thing we're going to do is just talk about graphing these points. How do I find these points out in space somewhere? So I made a worksheet for you guys. The link is on our little sheet that I gave you guys, the to-do list. It's on there, so you can print that up or you can look at it as we go, but we can plot some different points. So let's take a quick look-see at it here. I got to open it. I think it's right here. Yep. So here is our worksheet. And you know what? I'll just print it for myself. Okay. Make this bigger so you guys can see it. But here's our worksheet. Here we have all these points, A through H. I want to plot these things just to kind of get a feel for what polar coordinates look like. So for this first one, point A, I like to start in the direction. Okay, the direction is pi over 4 radians. We may need to review some of that, and you feel free to look in your notes or use that big wide internet thing and remember what pi over 4 radians is. It's 45 degrees. So we always start from 0, the positive x-axis, and we're going to rotate this thing counterclockwise until I'm pointing at pi over 4. Pi over 4 is right here. It's got this line for me. This graph I gave you was nice enough to break it into pi over 6's for me, 1 pi over 6, 2 pi over 6, 3 pi over 6. But we still do have the 45s in there as well. So pi over 4 is going to be this line right here. My positive values for r now are going to be in this direction. See, I'm using the end of my pen to give you where the positive directions are, because eventually you start seeing some up here. They're not positive, and we'll deal with that when we get to deal with that. But so I'm pointing at pi over 4, and then the radius, I want to go out 3 concentric circles, 3 units outward. So I'm going to go in that direction 1, 2, 3. That's where that point is. That's the point 3 comma pi over 4. That's point A. What I want you guys to do now is hit pause and try these on your own. So I'll back this up a little bit. Hopefully you can see most of the thing there. If not, feel free to open it. I gave you guys the link. But hit pause and go through and see if you can plot all of those points. Okay, we're back. Hopefully you guys tried that out. Let's take a look at some of them. I printed the answer key too as well for myself in color and everything, and fancy like that. But there's point A we already did. We can look at a couple of these and make a couple of generalizations. A couple of the trickier ones. 2 pi over 3, okay. 2 pi over 3 would be this way. And then I want to go a magnitude of 1. Ooh, that's a word for vector. Sorry. I'm going to go out 1 ring of my circles here, and that's why B is right there. 2 pi over 3, 1 right there. Okay. How about some negative things? Let's go look at point F. Point F says to go in the negative 4 pi over 3 direction. Going in the negative direction means we're going to go clockwise. We still start at 0, but then we're going to go clockwise with it. So this would be negative 1 pi over 3, negative 2 pi over 3, negative 3 pi over 3. Negative 3 pi over 3 is pi. Negative 4 pi over 3. So negative 4 pi over 3 is actually pointing in this direction, right? We're doing point F there. But then I want to go in the negative direction from there, okay? A lot of negatives here. Negative 4 pi over 3, I'm pointing in that direction right now. But then I want to go back 3 units. So I'm actually going to go in the negative direction here for my magnitude, or for my R value. I'm going to go backwards 3. So then if I go backwards 3, that's going to take me to 1, 2, 3. And I get F right here. There's actually 3 different points I gave you that all have the same location, but they're different coordinates. Okay, let's look at another one of those. How about H? We can look at H. H says to go in the negative pi over 3 direction. Negative pi over 3 direction is this way. And then I want to go out a magnitude of 3, or 3 circles. So I'm going to go out 3 circles. 1, 2, 3, and it's the same point. So we can have multiple representations for the same point, where in rectangular coordinates that didn't happen. 2, 5 is the only place where you can go to get to 2, 5. Here, because of coterminal angles, and this idea of positive and negative angles and positive and negative magnitude, or concentric circles, we can get to the same point. Okay, so take a look at that when you have some time. Make sure you can graph those. Next week is going to be graphing equations in polar form, and you got to be really good at graphing points. It's going to be a bunch of points that you have to plot and then play connect the dots with. Okay, so we're back here, and I have a general Cartesian point out here in space, and then I also have it in polar, right? Because I just got done talking about how we can represent the same point either with rectangular coordinates, x and y, or r and theta in polar coordinates. So what we're going to want to do now is kind of make a generalization. I want you guys to take a minute. You can hit pause if you need to, and see what connections are there. What connections are there between r and theta to x and y, where r and theta is our polar coordinates and x and y are rectangular coordinates? What theorems, what formulas, what ways do we have to connect these two things? Take a minute and see what you can think about. Okay, so hopefully you took some time and you came up with something. There's really 2 main things that are going to connect these guys. It's going to be the Pythagorean theorem, right? X squared plus y squared equals r squared. That connects x, y, and r. And then all of our trig stuff, all of our SOHCAHTOA stuff is going to be able to connect our r and our theta and our x or our y. Okay, so let's take a look at a couple of these. I think the first one I talk about is the sine of theta. If I take the sine of theta, our trig function, sine of theta equals the opposite over the hypotenuse, y over r. Okay, that's an equation that's relating these two things. Notice there's parts of Cartesian coordinates in there, and then there's parts of polar coordinates in there as well. That's relating the two. And we'll actually see it written like this, where I'll solve that thing for y, and I'll have y equals r times the sine of theta. Using the same argument, we could do cosine as well and get x equals r cosine theta. So now I have these two rectangular coordinates, x and y, in terms of polar coordinates. These two that I grouped here in green, those are the ones you're going to want to use if I give you something in polar form, polar coordinates, and ask you for the rectangular version. Those are the two we're going to use because you have r and theta, and you can just jam those in there and get your two values, your x and y values. Okay, the other one, as I mentioned a second ago, is the Pythagorean theorem. The Pythagorean theorem will be the other way. If I have x and y, how could I find r? That's the Pythagorean theorem. And then tangent. If I write the tangent of our angle, let's see if we can see the picture now. I don't need my blocker anymore. Tangent of the angle would be the opposite side over the adjacent side, y over x. So now on this equation, we can find theta if we have y and x. So these that I grouped here in this little peach brace are saying if you have rectangular coordinates, x and y, you can plug them into these little equations here and end up solving for r and theta. So going from rectangular to polar. So these are our 4 guys we're going to use the rest of this week and next week with these equations. We're going to use these guys a lot. They tell us a lot of information, and they're very, very useful. All right? So let's go into it. We have 2 types of problems now. If I give you something in polar form and I want you to write it in rectangular form, or the other way around. If I give you something in rectangular form and ask for it in polar. All right? So we're just going to go right into some examples. Here's my first one. Let's see here. Okay. There are 3 points. All 3 of them are in polar form. You have how far away and at what angle. How far away and at what angle. Far away, what angle. It's always a good idea. We're trying to find the X and Y equivalent, basically, for rectangular coordinates. I want to be at that exact same spot by going over how far and up or down how far. Okay, so that's what rectangular coordinates are. It's a good idea to practice just plotting these. If you make a little graph and plot these, you can kind of start to convince yourself about where to go, especially like on these first ones. Yes, these formulas that we went over just a second ago will work just fine, but it's a good idea to be a little aware of your situation. Do you understand what's going on and how to get to where you need to get to? So let's just go right into it. Let's look at the first one. This first one is saying to point in the pi direction. Okay, well, again, with this common sense type of thing, looking for some scratch paper here. Common sense type of thing, it's saying to point in the pi direction. That's this way. And I want to go out, what is it, -3 units? Okay, so if it's pi, these are my positives. Away from that would be negatives. -3 would be 1, 2, 3. This would be the point, -3, pi. Sorry, phone went off. Okay. If we stuck to formulas, okay, well, I need a formula. I'm more of a formulaic person. Some people are like that. You can use these formulas and you would get the exact same thing. But again, we're going to have to review some of our trig. The cosine of pi is -1. -1 times the -3, 3. Sine of pi, 0. 0 times -3, 0. And you get the same answer either way. But the more you know, the better you are at it. You're better. Okay, moving on to the second one. We're looking for the point 2, 3 pi over 4. Want to aim in the 3 pi over 4 direction, then go out 2 units. Okay, this time I'm going to go straight to the formulas. My x-coordinate is r cosine theta, so that would be 2 cosine 3 pi over 4. The y one would be 2 sine 3 pi over 4. That's not too bad, okay? We're going to have to review some trig, unless we remember what the cosine of 3 pi over 4 and sine of 3 pi over 4 is, and some of you should. But so what I did is I just drew 3 pi over 4 in here and labeled the sides that I remember. I had you guys memorize those things. A 1 square root of 2 is our pi over 4 stuff, and then based on where the quadrants are, that one's going to be negative. Okay, if I'm looking for the cosine, that's my angle. That's 3 pi over 4. The cosine would be the adjacent side over the hypotenuse. Okay, so adjacent side over hypotenuse, it would be -1 over root 2, and if I rationalize, that should ring a bell, -√2 over 2. That's the cosine of 3 pi over 4. If I times that by 2, the 2 down here and that 2 cancel, I'm just left with -√2. Okay, same exact argument for the sine of 3 pi over 4. Sine of 3 pi over 4, root 2 over 2, but I'm timesing it by 2 up here, and we get our point. Our point is -√2, root 2, exactly. If you just jam this in your calculator, you're going to get some decimal. It's an irrational number. Okay, I showed you guys over here in blue a different way to think about it. If I'm trying to find the point 2, 3 pi over 4, and what that is in rectangular coordinates, I started by drawing where it is. I know 3 pi over 4 is in this direction. I know I'm going 2 units out. I make a little triangle here where my x-coordinate and my y-coordinate. This is what we're looking for. Okay. Then what I did is I made the mini-me version. Okay, we're doing a lot of the same stuff here. 3 pi over 4 is a 45-degree angle. 1 square root of 2, with this one being negative. And now we have similar triangles. Think back in your geometry days. So from here I can set up some ratios to solve this thing. I can say x is to -1 as 2 is to root 2. Or I could say y is to 1 as 2 is to root 2. And I'm just setting up proportions there, setting those ratios equal to each other, and then solving them. So that's what I'm going through here. There's the x over the -1, or x is to -1 as 2 is to root 2. We go through it and we solve it and we rationalize, and you get the exact same points either way. Okay, so one is using trig, one's using similar triangles. Both of them kind of require you to remember our 1 root 2 stuff. So that's what we're looking at. There's that first one, okay? We'll come back and then that's my first video. We'll come back to the second video and we'll continue down this path. So I'll see you in a second.